All right, you don't have to write down this stuff. This is stuff we've had up here before, left, right, midpoint, trapezoid. But where we are at right now is we talked about a definite interval, okay? What does a definite interval mean? Well, it means area. But we're starting to see it means more than that. We've been doing that tabular, the tables of data packet, and we're starting to do these story problems, and we're starting to see that I can do as an integral. If I have a function that's gallons per hour, I can do an integral and give me the total gallons, or the net gallons, or whatever. And so we're starting to see some story problems as we do these packets and do some of these things. We're starting to see some of these story problems where you can use an integral to tell us actual values of useful type things, not just area under a curve, okay? Now, how do we do a definite integral? Well, we use fundamental theorem, but we know that's limited because you got to be able to do an antiderivative. And then you can do an approximation. Now, go ahead and get your calculators out. So and so we said there's three ways we could do it: geometry, fundamental theorem, and approximation. And then we added the fourth one, which is what? Use our calculators. Now that's our favorite one, and that's the one that we'll use a lot when we're doing these story problems. We'll set up our definite integral, and we'll just go with the calculator. But there's a little more we need to investigate before we just let the calculator do all this work for us. So if you look at your calculator here, all right, and let's say we were going to do an integral. So we've got geometry, but that hardly ever works. I mean, hardly ever does a function have a nice geometric shape so we can do the area. Plus, to do that, you have to have a graph of the function, and so we hardly ever have a graph of a function. Usually it's an equation or a table of data or whatever. So we don't have a graph very often. So doing the geometry is hardly useful at all. So fundamental theorem is good if you can do the antiderivative, but if you can't, we got to do an approximation technique. Now, doing approximation techniques by hand is kind of a pain, so we usually need a computer machine to do the approximation techniques for us, and that's where the calculator comes in handy. So when we say we're going to use the calculator to do these for us, let's just type in an integral here. Let's do the integral of, let's go 0 to 2. Let's do x squared, which of course is one that we know we can just do with an antiderivative. Okay, we hit enter, and the calculator gives us 8/3, right? Now that's an exact answer. The calculator did it with an antiderivative. Okay, the calculator knows how to do an antiderivative. Now, if we wouldn't have a CAS calculator, this calculator would have given you a decimal answer. Okay, matter of fact, well, I got one right here. Here's one that's not a CAS calculator. I said that it would do that. Now, as I say that, I'm not even sure, but I'm pretty sure. So if I go and do the integral, and I go 0 to 2 of x, where's the x? There it is. X squared dx. Everybody see that? 2.66666 is what it says. Okay?
Yep.
Right? Trust me? Okay. 2.666. All right. Now, so that's because it cannot do the antiderivative part. So what is that calculator doing? An approximation technique, right? Now, how is it getting that exact answer, 2.666? Well, it's only giving the exact answer out to, I think the max is 12 places, 12 digits, if we have our calculator set on float. Now, for you guys, you can just hit Control-Enter, and what the calculator is going to do is it's going to take that 8/3 and divide it and just give you the decimal. Okay, and it's going to go out with 12 digits there if you count. All right, the question for us is, how does the calculator know? How does that calculator know that can't do antiderivatives? Or how does our calculator know if we do one where you can't do an antiderivative? How does our calculator know that it's accurate out to 12 decimal places? That's what we're going to investigate here in chapter 6. Okay, now somebody said yesterday, well, it does infinite. It does a limit as n goes to infinity. Well, it actually doesn't quite do it that way. There's an easier way. As a programmer, there's an easier way to program it to give me 12 digits of accuracy than there is to try to set up a sigma and do the limit as n goes to infinity like we did last time. There's an easier way, okay? And so we're going to show you kind of how that works today. All right, now if you go into your calculator, well, let's type another one in. Let's do another integral. Let's go up and grab that last integral we had. Let's change it a little bit. Let's change the x squared. I'm going to delete that. Let's change that to sine of x squared. Now, this happens to be one, whoops, This happens to be a function that does not have an antiderivative. So when we hit enter on this one, notice what we get. We do not get an exact answer. It goes right to a decimal. So your calculator, and if we go into our, under doc here, and I go down to settings, number 7, and I go to my document settings, number 2, and I go down here to calculation mode, I see that my calculator is set in auto mode. Now, what auto mode means, here are the other choices. I've got exact or approximate. So auto mode says, I'm going to try to get an exact answer. And if I can't, I'll give an approximate answer. So like if I type in square root of 8. If I type in square root of 8 on this calculator, I think, now this actually, it might do that. I don't know. If I go square root of 8 on this calculator and hit enter, I get a decimal. If we do square root of 8 on our calculator, what do we get? How much? 2 root 2. We get 2 root 2. It finds an exact answer. We can force it to give an approximate answer by hitting Control Enter. But our calculator set in auto mode is going to find an exact answer using algebraic or calculus techniques. That's what CAS means. And then if it can't, it'll give us an approximate. And that's what's happening here on this integral. Now, I did this in the other class. Let me go to my document settings. Let me go to my settings here. And let me change this to exact mode. Hit enter. Hit enter. Now let me go up and grab this integral. And watch what happens when I try to do it. It says I can't do it in exact. I can't get the exact error. Okay? There is no antiderivative. So it just spits it back out at you. Okay? So that's why, of course, I'm not even sure why they give us that option. I don't know why you'd want to be in exact mode. Maybe you only want an answer if it'll do it exactly. I don't know. But so that's why we're always in auto mode. And so it'll give us an exact answer if there is one. And if there's not, it will give us a decimal. So that's what's happening here. All right, so what we're going to do in Chapter 6 is we're going to investigate this approximation technique a little more. And we're going to learn kind of how our calculator is working. The calculator is somehow knowing that that answer is accurate out to those 12 decimal places. How does it know? If there is no exact area that can be found. If there's no antiderivative, we can't do fundamental theorem part 2. We do not know the exact area. Unless we would do an infinite number of rectangles and kind of see what it's approaching. So how's it doing? Okay, how's it doing it? That's kind of what we're going to look at today. So you're going to hear me say a lot of stuff about things like how much error is there in this approximation? What's causing the error in this approximation? Okay, because what's causing the error is going to help us measure how much error there is. And if we have an idea of how much error there is, then we can know how close we are to the exact value. Okay? What's causing the error and how much error is there, and it's not going to, we're not going to know for sure how much error there is, but we'll know kind of a worst case scenario. For example, let's talk about left and right rectangles just a little bit. So let's go back to this page. Okay, so you got left rectangle. All right, a left rectangle, if this graph's going up like this, a left rectangle is going to be what? Underneath. It's going to be too small. Now, why is it too small? Or a better question would be, what kind of function would left rectangle be perfect for? Y equals a constant. A flat horizontal line, a left rectangle would fit perfect. Anything that's not flat, a left rectangle is not going to be good for. Now, what is going to make the error worse? Steeper. The steeper it is. And what do we have that measures steepness? The first derivative, right? The slope, if the slope is 3, that's steeper than the slope being 2. And the steeper it is, the worse a left rectangle is going to be. Does that make sense? So it stands to reason, and this is what's going to happen over the course of next week, it stands to reason that the value of the first derivative is going to have something to do with how much error a left or right rectangle will have. The steeper it is, the more error there's going to be. Okay? That's what we're going to be investigating here a little bit today. Okay? What is causing the approximation to be off, and how much is it off? Those kind of questions. All right. So anyway, back to what we had with left rectangle. So we height times width, height times width, height times width, right? We got the same thing here, same thing here. Of course, here we got our trapezoids. Now, first thing I want to do is write in our notes another way of writing this. I've already talked about it a little bit. You don't have to do them this way, but I think it's probably a good idea to start doing them this way. Today, what we're going to do is we're going to write a few out by hand again. Okay? Tomorrow, I'm going to give you a program for your calculator to let you do them automatically. The rule is going to be this. Our next quiz, you're going to have to do some by hand and some with this calculator. If you have single-digit subdivisions, you're going to do it by hand. If you have 10 or more subdivisions, we're going to let the calculator do them for us. Okay? So today's homework is going to be ones by hand. Tomorrow we'll do ones with the machine. All right, so here's what I want you to write out here. All right, so what we can do, we're going to assume right now that everything's equal width. Unlike the tables that we have, if you have a table of data, you're probably going to write it out like this. Height times width, height times width, height times width, because the widths aren't always equal. But let's assume for now we have equal width. So I can factor out the width. And remember, the width, delta x, is b minus a divided by n, right? That's the width. Okay, so if I would do that, then another way to write lefts would be this right here. Let's write that down. So we're going to factor out the width. We're going to write b minus a divided by n. And then we'll have f of x sub 0, f of x sub 1, f of x sub 2, all the way to the one short of the right edge, right? Okay, so this is just another way of writing a left approximation. But it makes things easier for us because we don't have to write the width every time, right? Instead of f of 0 times 2/3 and f of 1 times 2/3 and f of, well, it wouldn't be that, I guess, if the width was 2/3. But you get my idea. We always would write out that width, and I'd make you do it. Why? Because we were doing sigmas, and we wanted to see the pattern. Well, now it's not going to be that big a deal. We're not going to write sigmas, so we don't need to see the pattern, right? So it's good to do this. We just factor out the width, save ourselves some writing. Okay, rights will be pretty much the same thing. We'll factor out the width, except this time we start at x sub 1, go to x sub 2, and we end at the far right edge, x sub n. And we're going to do an example here and show how this works. Okay? So there's a left rectangle, a right rectangle, and then a midpoint, we do the same thing, right? I mean, first midpoint, second midpoint, third midpoint, they all have the same width. We just factor out the width, the b minus a over n, then f of m1, f of m2. Okay, this is just an alternate way of writing it. Now, I don't care. If I tell you to do an L3 in the homework, and you want to write height times width, height times width, height times width, that's fine. Or you can pull out the width and do height plus height plus height. Because that's basically what this is, right? We're pulling the width out front, height, height, height. Now, how many of these are there? How many of these heights are in here? No. There's n. There's n items in here. So if I'm doing an L3, I should have 3 heights in there. And if I'm doing an R3, there should be 3 of those in there. And the same thing with an M3. I should have 3 things in there, right? 3 heights, because I've got 3 rectangles. All right, now. But if there's 6 subdivisions, for example, there'd be 1 midpoint, 2 midpoint, 3 midpoint, there'd be 6 midpoints. Oh. Yeah, so that's what the end is there. Okay, now let's talk about trapezoid. So the trapezoid, we know from before that if we, and I talked about this and I showed you on our last quiz how you could do this. If we factor out a 1/2 and factor out the delta x, then there would be a 2 down on the bottom here of this b minus a over n, right, because of the 1/2. And then we had f of x sub 0, then we'd have 2 f of x1s, right? We'd have 2 of all of them except the first one and the last one. Remember that? Okay, so that's what we get here. So that's what I have written out here. So I have b minus a over 2n, right? This is just an alternate version of the trapezoid. Now this one's actually definitely one I think you want to know, because instead of writing out, if you have to do 6 trapezoids, it just takes a while to write out 6 trapezoids. It's much faster to write this out. Okay? So we have f of x 0. We start at the far left edge, and we have 2 of those, 2 of those, 2 of those, 2 of those, and then 1 of the last one. Now, how many items are going to be inside of there? How many of these heights? If we have a T6, how many of these are in here? No. X sub 0, X sub 1, X sub 2, and it's going to go all the way to X sub n. So you're going to go all the way from, if we have a T6, for example, you're going to go all the way from X sub 0 to X sub 6. How many is that? Here, let's say we start here. X sub 0, X sub 1, X sub 2, X sub 3, X sub 4, X sub 5, and X sub 6. So if we have 6 trapezoids, right? One, two, three, 4, 5, 6. Isn't there always just one more? Because you're using both the left edge and the right edge, right? And we start at 0 and go to n. So you're always going to have one more. It's n plus 1 items is what you're going to have. You're going to have n plus 1 items, okay? You're always going to have just one more because you're using both the left edge and the right edge. You're using double all those other ones. I'm not, but again, when I say items, I'm not counting this as 2, I guess is what I'm saying. I'm not counting this as 2 items. I got 1 and 1 and 1 and 1 and 1. Right now, like I said, 5 of the 7 have 2's in front of them, and the first one, the last one, don't. Okay, but you're always going to have one more item when you do a trapezoid. Now, here's something else I want you to write down right here. We've talked about this before, but we never really formalized it. This is a valid formula to use for trapezoid. If you need to do a T6, then you can take an L6 plus an R6 and average them. Because that's what a trapezoid is. And I think I showed you this picture before, but basically if I have a left rectangle here, and I've got a right rectangle here, the trapezoid is simply an average of those two. Okay, the left is too little, the right is too much, the trapezoid is the average. Now, that makes sense that that'd be a good thing to do, right? Because if lefts are under, we know rights will be over. They're kind of like partners that way. If lefts are under, rights are over, if we average them, that ought to be better, right? And if lefts are over and rights are under, average them, that ought to be better. So the nice thing about a trapezoid is it's just a better approximation than a left or a right, okay? Now, so there's nothing really new there. All right, so what I want to do is before I go into kind of the newer stuff, I want to talk about a problem here. So let's talk about this problem right here, because a couple of your homework problems are going to be like this, where we have to do some stuff by hand. So you might want to, now we got some stuff we're going to add to what we just did there, so you might want to go to the next page or something to do this problem here. Okay, because we're going to come back and add to what we were just doing there. But I want to look at this first. Okay, you see down there at the bottom I had S6, and that's something we're going to get to here in a minute. All right, but let's look at this. So we got this integral. Now, obviously, this is one we know the exact answer to, but sometimes we're going to do that. We're going to do it with ones we know the exact answer to. But we're also going to do it with functions where we don't. Okay? And we're going to get to use our calculator, so we'll have those handy and ready to go. All right, so the first thing they're going to ask you on a couple of your homework questions is going to be, find the exact answer. Okay? And I, they use I a lot in this section. I for integral. So I is like the exact answer. I is the exact answer. I is the integral. Okay, so it's the exact answer. Well, this one is easy, fundamental theorem. So they're going to ask you, hey, find the exact value of I using a fundamental theorem. So we get 1/3 x cubed, right? Some problems we won't be able to do that. Of course, if you can't, they won't ask you to. Okay, and then we get 8/3 minus 0, which you know is 8/3. And I'm going to write it as a decimal. Let's go 3 decimal places, 2.667. Of course, it doesn't hurt to draw a little picture of what we're talking about. We're talking about a parabola, 0 to 2. We're talking about this piece of area right here. Okay? So, That's our exact area. Okay. Now let's do an L3. So one of the things it'll ask you in the problem, it'll say write out an L3 and R3 and M3. Okay. Let's do it with the new versions that we've had today. So L3 would be, we'd have B minus A, so that'd be 2 minus 0, divided by 3. That's our width, right? So our width is 2/3, right? So our width in this problem is 2/3. That's always one of the first things we wanted to calculate anyway. 2/3. Now I could do height times width, height times width. I could do it the way we did it before, but let's try this new way. So what do we do for a left? We start where? Let me put those in here. So we got 3 subdivisions, so we're going to start our left at 0. So let's do F notation. Let's go F of 0, because we're going to use our calculators to help us here in a minute. So let's go F of 0 plus F of 2/3. The next one over would be 2/3. The next one over would be 4/3, and then this one would be 6/3, but I don't care. I'll call it 2. I'm not writing a sigma, so I don't really care about patterns right now. So it's going to be F of 2/3 plus F of 4/3. Notice I don't put any widths on these because I pulled the width out in front. Do I stop right there? We stop short of the right edge, and look how many we have in there. 1, 2, 3. Yeah, 3 rectangles. There should be 3 heights in there. That's what those are. Okay, now, let's go to our calculators. Let me show you what we're going to do with our calculators to let our calculators do some of this work for us. All right? Is everybody ready? We're going to go into the menu. Number 1, actions. Number 1, define, or I could just type out define. And let's define the function f. F of x equals x squared. And so whenever I start a problem like this, I'm going to define my function like that. So all I have to do is type the F notation. I don't have to type all the function messiness that's going on there. So I define my function. Now, what I'm going to do here is now I'm going to do 2/3 times, and then in parentheses, I'm just going to go F of 0. Because you're going to see the advantage of doing this, because here in a minute, we're going to be able to basically just grab this and repeat it. And then what do we have? F of 2/3. And then plus F of 4/3. And I want a decimal, so I'm going to hit Control Enter. 1.481. Right? 1.481 is what I got. 1.481. Now, that's way under the exact answer. Why? Because the function is increasing, right? Therefore, lefts are going to be under. Some of your homework questions today are going to be like that too. They're going to give you a function. You're going to have to graph it so you can tell, is the function increasing or decreasing? You're going to graph the function, look at it, and they're going to ask you if lefts are under or over. And you're going to have to say which and tell why. Well, if it's under, it's because it's increasing. If it's over, it's because it's decreasing. Right? Increasing and decreasing is what's going to tell us that, which, of course, is when f prime is positive or negative. Right? The first derivative is what's telling us whether lefts or rights are going to be under or over. Okay? We're going to formalize that in our notes here in a minute, but it's a pretty basic idea. Now let's do our right. This will go pretty fast now at this point. So we got 2 minus 0 over 3. And then what are we going to have in here for the rights? We'll start with 2/3 and then go to 4/3. And then the last one will be f of 2. Right? So we don't use the first edge when we're doing rights, and we go all the way to the final edge, and again, we have 3 items in it. Okay? Go ahead and type that into your calculator. All you got to do is grab the one from before, change the f of 0 to an f of 2. Right? So having that f notation, having that in there, it saves us a little time. 4.148. Way too much, which of course we knew it would be too much because it's increasing, and so rights are going to be an over approximation. Okay? Now, what about our midpoint? Well, I'm going to go into my little graph picture here, and I'm going to put in my midpoints in red here. Okay? So we got midpoints now. So so we're going to have 2 minus 0 over 3 again, right? Because it's still the same width, right? We're still only doing 3 of them. So right? So it's 2 minus z, b minus a divided by n. So the width is still 2/3, right? What's my first midpoint? 1/3, right? Halfway between 0 and 2/3, 1/3. What's my next midpoint? Halfway between 2/3 and 4/3. That'd be 3/3 or just 1. Because I don't really care about patterns right now. We're not doing sigmas, so you can write 3/3, whatever. Last one is 5/3. Okay? Right? So again, height times width, height times width, height times width, or what we're doing now is we're just pulling the width out in front and we're putting in the 3 midpoint heights. And we type that in? 2.593. Pretty close. Midpoints are better, right? Makes sense, because a midpoint, a piece of the rectangle will be above, a piece will be over. So we already said, well, why don't we just do midpoints anyway? Well, we're going to talk about that here in a minute. Okay? So pretty close. Pretty close. All right? Midpoints are just going to be a little better, because part of it's going to be over, part of it's going to be under. All right, trapezoid. Now, I want to write this out both ways. I want to write it out the long way, just because I want to just practice doing that. But if I was really doing this on a quiz, and I've already done L3 and R3, then wouldn't you just use this? Right? If I've already done L3 and R3, just average them, and that gives me T3. Don't do it the long way. Now, if the question just was find T3, then you got to decide. You want to do L3 and R3 and average them, or do you just want to write out the long way of T3 just to get it in one shot? That would be up to you. Okay? I want you to know both. Okay? So let's write it out the long way first. So we're going to go, what was the formula? It was 2 minus 0 over 6, right? 2 times 3. Right? Remember, this trapezoid is b minus a over 2n, because that 1/2 is out there in the trapezoid formula. All right. And then what are we going to have in here? We're going to start at the left edge, f of 0, to f of 2/3. We're not doing those midpoints, right? We're just doing the blue ones up here. I don't know why I'm doing this in red now. We're doing the blue ones. So we got 2f of 2/3, 2f of 4/3, and 1f of 2. And how many do I have inside there? I have 4 of them. If I'm doing a T3, I'm going to have 4 of those heights in there. I'm always going to have 1 more. So I know that I've got, so the first one is 1, the last one is 1, and the ones in between I'll have 2. Okay, so we can type that out, or we can just trust that if we would have let's do the shortcut now. The shortcut is L3 plus R3 divided by 2. Now it has to match the T3 there. So L3 plus R3 divided by 2. So now if I was doing this, guys, I would go up to my calculator and grab the ones that were not rounded, right? I wouldn't type these in. I think you should go back up and get your L3 that was unrounded, get your R3 that was unrounded, add those, divide by 2. What do we get? 2.815. Either way, we should get 2.815. Right? They're both appropriate to use. Either one is fine. Right? You good there? All right, so these are just alternate ways now of doing the same approximation we've done before. But here's where the calculator comes in. Writing them this way for a programmer, this gives a pretty nice formula to be able to do. We can find the width, we know our subdivisions here, and then the thing we'll be studying later on is how many subdivisions do we need? If I want 5-digit accuracy, how many subdivisions is it going to take? And that's where all this stuff with derivatives and stuff is going to come in. Okay, so we got several days to go before we get into that. Probably, as a matter of fact, it'll be next week. But just laying the groundwork for how this is working. Okay, now I want you to notice something about midpoints and trapezoids. Look at those two answers. One's under, one's over. Interesting. I don't know that we've ever talked about that yet. With lefts and rights, they are a pair. If one's under, the other's over every time. Midpoint and trapezoid are also a pair. If midpoint is over, trapezoid's under, and vice versa. Now we know trapezoid's a good one because it's an average of left and right. One's under, one's over, we average them, we ought to get a better one. But unfortunately, it's also going to be under or over. So if now, what happens if we took midpoint and trapezoid and average? Be even better. Okay, so we're going to get to that in a minute. Now, before I do, I've got something I want to just kind of, and I don't know if you need to write this down, but there's something I want to hit upon with this midpoint trapezoid over-under thing. First of all, okay, left. If the function, or excuse me, if f is increasing, right? Yeah, what's a left going to be? Under. And a right is going to be over. If the function is decreasing, it's the opposite. Left over, right under. Okay? Little picture of that. Easy. Left under, right over. Function's decreasing. Oops. Left is going to be over. Right's going to be under. Okay, so pretty easy to tell. What is it that causes a trapezoid to be under or over? Let's do over first. Concave up. That is right. Think about this. If a trapezoid, if you had a function that's concave up, isn't a trapezoid going to do that? It's the curve that causes a trapezoid to be over. Right? And if it's concave down, a trapezoid's got to be under. Right? Trapezoid's got to be under. It's the curvature. Now, remember what we said earlier with a left and a right? What fits a left perfectly? A horizontal line. If it goes up at all, then the left doesn't fit anymore. And so it's the slope that's going to determine how much error we have. What kind of a curve would a trapezoid fit perfectly? Any kind of line, even a diagonal. A trapezoid is going to fit perfectly. But if it curves at all, it's not. What's going to determine how big this error is? How much it curves. How curvy it is. Aren't some curves curvier than others? Yes. Curvier. Right? Yeah. Some are curvier than others. What measures the curviness? Second derivative, right? Remember when I don't know if we've ever talked about this. If second derivative is 3, and another function has second derivative of 4, they're both concave up. But this one's more concave up. It's got more curve to it. Now, we always knew that with slope. If you had a slope of 3 and a slope of 4, this one's going to go up steeper, right? But same thing's true with second derivative. So, first derivative is going to determine how much error left and rights have. Second derivative is going to determine how much error trapezoids and midpoints have. Because it's the, now we haven't talked about midpoints yet, but it's the curviness, the amount of concavity that causes the error. Okay, so that's something we'll be getting into a little more later. But we already know, I've already told you that, and I haven't told you why, but if trapezoids are over, I told you that midpoint's got to be under. Why? Well, I think that's true. I mean, let's look at this. So if I have a midpoint's going to look like this. Right? Now, is this going to be under or over? Well, it turns out it's going to be under. Because a trapezoid would be over. Is it because, yeah, as this curves away, we're getting extra here compared to here? Because this is curving towards, right? Doesn't that make sense? It's kind of curving towards this part, where this is curving away. And so this is going to be a little bigger than that. I would agree with that. It is that curviness that's doing it. But here's a really cool way to see it. We're going to think of a midpoint rectangle. Here's a midpoint rectangle. I'm going to take this top piece right here, and I'm going to pivot it like this. Now, tell me what you think about this blue area compared to this red area. You think they're the same? Wouldn't this triangle be the same as that triangle? In geometry, those are called congruent triangles. Side, angle, side. Right? That's what we would get there. Those are congruent triangles. That's true. The blue area is the same as the red. So here's the lesson. A midpoint rectangle equals a pivoted trapezoid. A midpoint rectangle is a pivoted trapezoid. Okay? So what that means over here is, and now watch this happen. Now, you're not going to have to do this every time or anything. You just have to understand. I just want to show you why midpoint trapezoid are opposite. Okay? Because look what happens if I pivot this top piece. It would pivot. Oh, this is bad. Pivot. Pivot. Isn't it under? Wouldn't it actually be tangent to the curve? It would just touch the curve at that midpoint, and we take that top piece, we just pivot it, and it's going to be under. And if it was the other way around, if it was this, and you had a midpoint rectangle, and then you pivoted this, oops, it would be above, wouldn't it? It would be above. So, now in green, let me do with a trapezoid. If I was actually doing a trapezoid here, wouldn't it be here? Trapezoid would go there to there. Trapezoid would be over if it kind of came up. The midpoint rectangle, if I pivot that, it would actually be under. So when you look at it that way, you can say, oh yeah, that's why midpoint and trapezoid have to be opposite. Now, which one of these is going to be better? For this rectangle right here, is a trapezoid going to be off more, or is a midpoint going to be off more? I think the trapezoid's off more because doesn't it curve away from the trapezoid? Whereas this curves kind of towards the blue line. That's exactly right. So remember I said we're going to average them, right? If the midpoint's over and the trapezoid's under or vice versa, wouldn't it make sense to average them? Wouldn't that be a better approximation? It would. But here's the problem. If the trapezoid is more over and we average them, what's our answer going to be? It's going to be too high, right? Now it's going to be better, but it's going to be too high. It turns out that the midpoint is roughly, not exactly, but roughly half as much air. Twice as accurate, right? Half the air. So it would make sense to do a weighted average. In other words, if we do a trapezoid, we're going to have double the amount of air. So if we do two midpoints, does that make sense? So we'd have this amount off over. If we do two midpoints, we'd have roughly the same amount under. Then we average them, we would get a pretty good approximation. And so that's called a weighted average. So what we're going to do is we're going to take, for our formula, right here, so you can copy this part down right here if you want, and then we're going to come back and talk about this. This is called Simpson's rule. That right there. It's called Simpson's rule. Now, you're going to notice, go ahead and write down what I have here, this 2n. Write this 2n, and then the n's there. Okay? And while you're writing, I'll just talk about it. So this is called a weighted average. So we're going to take two of the midpoints, because they have half the air. So we take two of those, and let's say it's under, and then add that to the trapezoid, which is over, and then divide by 3. Right? So it's a weighted average. This should give us a pretty good approximation. That's called Simpson's rule. Simpson's rule. Now, here's the thing. If you do an M3 with a T3 and do this weighted average, that's actually an S6. Now, here's why. Because we're averaging midpoint and trapezoids, and if you think about it, the trapezoids use the blue, and the midpoints use the red. So how many subdivisions do you end up with? Twice as many. You end up with 6. So a Simpson's will always be an even thing. You will never be asked to do an S7. It's always an S6 or an S8 or an S10. Okay? So if I'm going, so let's go ahead and go down here and finish this. So this is why in this problem, when I did an L3, an R3, an M3, and a T3, this is why that same problem would ask me for an S6. So an S6 is going to be an S6 is going to be 2 M3s plus a T3 and then divided by 3. Or an S8 would be 2 M4s plus a T4 divided by 3. Right? Or an S10 would be 2 M5s plus a T5 divided by 3. All right, so go ahead and do that. Grab your unrounded values. So grab 2 times your M3 plus your T3. Divide all that by 3. What do you get? Oh, isn't that interesting? It's the exact answer. Now, that turns out to be well, there's a reason for it. It's not really a coincidence. But it happens to be just specific to this function. We said left and rights fit what functions perfectly? Constants, horizontal. Trapezoids and midpoints fit what perfectly? Any line. A midpoint would too, right? Because a midpoint, if you pivot it, it would fit perfectly, right? So midpoint and trapezoid would fit any line perfectly. It turns out that Simpson fits any parabola perfectly. Any second degree function perfectly. And actually, it even goes one step farther than that. It fits any cubic function perfectly too. But a fifth degree or something that wouldn't, and a sine or an e to the x, it wouldn't fit perfectly, but it's pretty darn good. Simpson's rule, or it might be an altered variation of Simpson's rule, is what's programmed into your calculators actually when it does these approximations. Okay? Now, we're going to do a few by hand, but we'll see later, how if we did 100 of them or whatever, we can get a pretty good approximation. Now, there is a long version of Simpson's rule. All right? There is a long version. This is it right here. Let's write it out with me. The long version of Simpson's rule is this. B minus A over 3n. So this would be 3 times 6 in this case. Because we're doing an S6, right? I realize we talked about this being 2n in our other formula, and then this was n, okay? But forget the short version for a minute. Now we're just doing an S6. So now we're thinking of the 6 as our n. Okay, we're not doing the shortcut version, so I'm not caring about that at all. So it's 3. The 3 is in there, because remember our weighted average where we divide by 3, that's why it's in there. I'm going to show you that in a minute. And then times, we're doing S6, so it'd be a 6 there. And then in here, we're going to have f of 0. It's a lot like trapezoid. Remember the ones we said we got to use? We got to use all these up here, right? We got to use all these. The midpoint, we got to use the blue and the red. So we'd have f of 0 plus, now, wait a minute, don't write it yet, but what would be the next one? 1/3, but there's 4 of them. 4 f of 1/3. Plus 2, what's the next one? F of 2/3. Plus 4 f of 3/3, which is 1, plus 2 f of 4/3, plus 4 f of 5/3, and then the last one, there's just 1. That'd be f of 2. That's the long version. It's like trapezoid, where the first and the last one we only use once. There's 7 items in there, n plus 1, and the pattern inside is 4, 2, 4, 2, 4, and the last ones will always be 1. It'll always be 4 at the edges as well, right? Right before the 1 and right after the 1 at the beginning, there'll be a 4. 4, 2, 4, because there's an odd number over. Now, where in the world does that come from? It looks like the midpoint ones were the ones that had 4s on them, right? The other ones had 2s. Because you use it twice. Now, it's a little more complicated than that, but that is where that comes from. Now, I would like to walk through that with you. Don't write it down, please. Okay? It's too much. But I want to go through, because in the past, on the years where I haven't went through this, I think people, they see the 424 and it's like, what in the world's going on? So I just want you to see it. So I've written this out. So let's say we have 6, right? These are the trapezoid ones, those in there are the midpoint ones, and so I've numbered them like so. Okay, here's our formula for an S6. 2 M3s plus a T3 divided by 3. Okay, so I've written out my M3. Okay, here's my M3. My M3 is going to use X1, it's going to use X3, and it's going to use X5. Everybody with me there? And then we got B minus A divided by 3, right? B minus A divided by N. N is 3 right now because we did M3. Okay, here's my T3. So I got B minus A times 2 times N, 2 times 3. And then I use X sub 0, I use X sub 2, X sub 4, and X sub 6. But I do 2 of those, 2 of those. Okay, now, next page, I'm going to add these up, but I got to do 2 of the M3s. Okay? So here's, now ignore that red just for a minute. So here's 2 of the M3s. So I got my B minus A divided by 3. But then I got to multiply by 2. So I'm going to move the 2 through the parentheses. So that's where those 2's come from. Okay, so I multiply by 2. So the question is, well, how did 4 get there? Right? Well, now I want to add these together. But I look at this and I can't add those together because these don't have common denominators. Right? Because the trapezoid has a 2 down here. So what I need to do is do a 2 times a 2 up here so they have common denominators. So now when I do that, I got my 2 times 3 down here. Now this 2, what am I going to do with that? Distribute that through. So that becomes a 4 and a 4 and a 4. That's where the 4 comes from. Now when I add these together, so now I got B minus A over 6. See how that becomes a 6? Now remember, this is S6. So that's where this 6 comes from. That's why this 6 matches that 6. Remember, these were S3, M3s, and T3s. This is 6. And now look what I got. I got an X sub 0. I got 4 of these because I distribute that 2 through. So I got 4 of those. I got 2 of those, 4 of those, 2 of those, 4 of those, 1 of those. Right? That's what happens when I add them up. Now, what I haven't done yet is divide by 3. Because remember back here, we got to add these up, then we got to divide by 3. Okay? So I divide by 3, and so that's where this 3 down here comes from. So that's how we get, for an S6, we get B minus A over 3N, and then we get this pattern with the 4, 2, 4 thing. That's where it comes from. Okay? So if we looked at, if we added those up. All right. Anyway, so you either can memorize this Simpson's rule the long way, you can do the short way. So if I ask you on a problem to do an S8, you got a choice. If you've already done M4 and T4, good, use the shortcut. If you got to do just a plain S8 by itself, and I think one of your homework problems you do, then you got a choice. You can either write out the long version here, or you can do the M4 and the T4, and then use this. To be honest, the long 4 is probably shorter than doing both of those and then add them, but it's up to you, right? But that's Simpson's rule. Simpson's rule is a better approximation than any of these, just a little longer, whatever. That's Simpson's rule. All right. So we only have just a little bit left, and then I'm going to let you work. So we talked about what causes over and under. Concavity causes the over-under on trapezoid midpoint. Okay? Increasing, decreasing causes the over-under on these. All right, so you're going to be asked some questions about which one's over, which one's under. Or they're going to say this one's over, true or false, that kind of stuff. So those are pretty easy questions, I hope. You're going to have some homework questions, a couple where you have to write this out a little bit. 3, 4 subdivisions, not a lot. Okay? And then there's just some notation I want to make sure we understand. So jot this down real quick. So you're going to see some of this notation right here. Okay? Now, what was I? The actual area. That was the integral itself. So this is the actual exact area. Sometimes that's an amount we don't know. Sometimes that's an amount we do not know. Okay? What is the L sub n? Left, but that's our approximation. Now I could do the same thing with rights or midpoints or trapezoids in here, right? But that's our approximation. So if we subtract those, what's our answer then? What name could we give our answer? The amount of error. Okay? So when you see these bars and I minus L sub n in there, what they're asking for is the amount of error. Because in some of the homework problems they say find I minus L3. Well, they want you to do the L3, compare it to the exact, subtract them, find how much it's off. That's all it is. It's just subtract the actual from the approximation. That's it. Now, why are the bars there? Yeah, right. But I mean, why? What does that do? Yeah. If you got a negative here when you subtract it? What's that mean? It means this one's too big, so it's over. If you get a positive, it's under. But when we do this, all we care about is how much is it off. We don't care if it's under or over, right? If we're putting the bars around it, we're just saying, I don't care if it's negative or positive. I don't care if it's over or under. I just care how much is it off. So that's why the bars are there, right? They just say, okay, how much is it off? Okay, the amount of error. All right, so you'll see that in some of your notation. So let's go to your book. I gave you that assignment sheet. So let's just talk about some of these problems here. I did give you the assignment sheet? No? No. Sorry. All right, you can see chapter 6 is a little shorter chapter than what we just got done doing. Okay, we're doing that top line. Next one. Oh, yeah. Well, you never know, Roland. I would think after seeing this today, like I want to come back for more and see what tomorrow's like. All right. So the first two problems have a little bit of what we were talking about. They have you do an L3, R3, T3. They have you do an L4, R4. So you're going to get a little bit of this working it out by hand. Okay, which was this stuff here. Okay, so you're going to have a few like that. But then those are the longest ones. 1 and 2 are the longest one, and I think what's the other one? 14. 14 has you write one out by hand. 3, you don't really have to write anything out by hand. It has more to do with less than, greater than, which is like over, under. So there's going to be, so when you get to 3, you get to 15 through 18, you get to 29 through 34. Those are just questions that are like some true, false, or is it over, under, that kind of stuff. So you're going to be looking at the concavity, or is it increasing or decreasing. So go ahead and graph those functions on your calculator so you can see. Is it concave up, concave down? Is it increasing? Is it decreasing? What's going on? Okay? And then on the last one, 51, it talks about divide and conquer. Well, I want you to turn back to page 378. Example 6 talks about divide and conquer. So when you get to problem 51, go back and look at that example in the section to help you try to understand that. That's page 378. It's just like one page back. It's example 6. Okay? That was for problem 51. That's for that last problem. Okay? So you got a little bit. I'll leave this up here. You got the first couple problems. We're doing some of this. I think practice writing them out kind of this new way where we pull the width out in front. And then there's, these over-under kind of questions as well. All right, rest of the time, you can work. Is there anything going on Thursday? Anybody gonna be gone Thursday? Okay. All right, so because we got that assignment, a week-long type assignment that I'm going to talk about, so maybe I'll need to talk about that on Wednesday.
I'll be gone next Thursday.
Next Thursday, Friday. Okay.